Hello everyone, and welcome back to another video. First one since school has started for me. That's fun. But today we have a cool little integral here, and we're going to be doing another combo of both complex analysis and Feynman's technique. So let's get started. The first thing I'm going to do is, as I sort of said, Feynman's technique. We're going to introduce a variable t into this integral. So we're going to say this right here is now a function of t. So f of t is now equal to the integral over all real numbers of natural log, but notice it's tx squared, meaning that if we differentiate, right, f prime of t, this right here is equal to, well, still the integral over all real numbers, but the natural log is going to go away. So, and by chain rule in the numerator, we're going to have an x squared, dx of course. And then the denominator, our x squared plus a squared, is obviously going to remain the same, but by differentiation of this natural log, we're going to have a tx squared plus b squared right here. And what we're going to do now is just the complex analysis. So the contour we're going to be using is the following, just the usual semicircular one. So this right here, this way. And unlike normal, sort of, we have two poles actually, one at AI, not AI, but A times I, and another one at, I should write these down, at AI, but then also another one at B over the square root of T times I. So let's go ahead and find the poles or the residues at both of these poles. So we know that the entire line integral is going to be equal to 2 pi I times the sum of the residues. So let's start with the AI, shall we? We're zooming in on this bit, so the residue at AI. Well, this right here is just going to equal the limit as x approaches, I'm at a little bar here, AI of x minus AI, and then literally just that entire function. So x squared, or I say function, integrand, x squared, and then we have x squared plus a squared, tx squared plus b squared. And you'll probably be familiar with this. This can be factored as ai plus x. I wrote that backwards, but that's okay. X minus ai. And these right here, these terms are just going to cancel. And plugging and chugging, we see that the residue is actually just negative a squared over 2ai, and then times b squared minus t a squared. So that right there is the residue at ai. Let's find the residue at b over root ti. Goodness, that's a mouthful. Though not as much as some other videos. Anyways, the residue at b over root ti. Well, let's get to it. So it's going to be the limit as x approaches b over root ti, and of x squared, of course, x minus this term. It's kind of fun to say. And then the denominator also doesn't change. But to kind of save time, I'm also going to just factor it straight off the bat. So you'll see that we have a t x squared plus b squared, which by the nature of the coefficient in front of this x being an implied 1, I'm actually going to factor out a t real fast. So I'm going to say all this is multiplied by t, meaning that this bit right here is actually just going to become an x squared plus b squared over t. Meaning that whenever we factor this, we're going to end up with an x plus b over root ti. And then the same thing, but, the complex conjugate. So, or conjugate, you get the point. X minus b over square root of ti. And you'll, again, see that these cancel right here. So we can just plug b over root ti in at this point. And I'm going to put the factor of 1 over t out front right here. And you'll see that we have a b squared over t, or a minus b squared over t, pardon me. And in the denominator, we have a squared minus b squared over t. And then multiplied by 2bi over t, root t, pardon me. And what we end up doing with both these residues is adding them up. So let's try to get them at least in some sort of similar form. The first one actually isn't too bad. I'm just going to clean this bit up right here. So what I'm going to do is actually just distribute a t real fast and say this is now, well, we still have negative b squared over t, but I'm just going to distribute this right here. And we can also move this up, by the way. So really it's to divide by the square root of t. So we end up having a squared times t, and then minus b squared. And then times 2bi. And you'll see here actually that the denominators are very, very similar. Just one has an a and the other one has a b. So let's just go ahead, add them together, and get them to a common denominator real fast. And now that we have the sum of our residues, we can see that the 2i and the 2pi I right here is actually going to cancel with a couple terms in the denominator. So we're going to cancel all of these terms right here. And the next thing we're going to do is actually note that we have an a here, an a squared here, and a b squared, and a b squared, or b here. And that these are also going to cancel. So that a is just going to become, a squared is going to become an a, and this b squared is just going to become a b. So to get this to actually a single common denominator, the next thing we can do is just distribute this minus sign, which I've already done when I wrote that down. So now, writing it all out, we find that we now have b over the square root of t minus a divided by, there's a pi out front, b squared minus ta squared. And to simplify things a little bit more and to get this into a form where we can actually factor this, I'm going to multiply the top and bottom by the square root of t, meaning that this right here is going to go away, and that we're going to have a factor of square root of t there, and also one in the denominator. And the reason we're doing that is, well, quite simple. We can factor this term right here into b plus square root of t times a times b minus the square root of t times a. And you'll see that these factors right here cancel with each other, actually leaving us with pi over b squared, or sorry, b plus the square root of ta, and then we just have the square root of t. And this is the value not of our integral, but the value of f prime of t. So this right here is just f prime of t. And let's just think back. What did we actually need to find? We wanted just to find normal f of t. And to do this using Feynman's technique, usually we choose t in such a way so that t of 0, or f of 0 is just 0. That way we don't really have to worry about the constant of integration. But in this case, it's not necessarily so simple, because if we examine f of 0, what we find is we still have an integral over all real numbers, but we just have natural log of b squared. I'm just going to kind of move the 2 down, over x squared plus a squared, dx. And clearly, this is not 0. This right here we can actually evaluate quite simply as just being, well, 2 natural log of b. But then we have this extra term, divided by a here. Then we're going to have inverse tangent of x over a, evaluated from negative infinity to infinity. And what this simplifies to actually is just going to be a 2 pi natural log of b over a. Sorry, I wanted to include this inverse tan thing here just to show a little bit of work. A change, perhaps. But anyway, the point is f of 0 right here is not 0, because clearly this term right here is not always 0. So the question becomes, what do we do with this not being 0. And it's actually not awful because we can scroll down here. And, all right, this out right here. We know f of 0 is equal to 2 pi natural log of b over a. And perhaps I was jumping the gun a little bit here. We do need to actually evaluate that first. So let's actually just keep that in our back pocket at the moment. But let's just integrate this real fast. It's really not too awful. Just let u equal the square root of t. Du then equals, well, 1 over 2 square root t. Meaning that we have a 2 times u here equals dt. Thus, our integral is just going to be 2 pi times the integral of 1 over b plus au du. And this right here is actually one of the simpler integrals we've evaluated on this channel. This is just going to be 2 pi over a natural log of a plus b. Or, pardon me, au, or b plus au. We'll keep it consistent. And then plus some constant c. So this right here is going to be equal to some f of, well, f of u, really. Well, sort of. The u is a t. So f of some t, and this right here is just going to be some t squared. So what we have then is an initial condition. So this f of 0 here, and then also a function where we need to determine this constant c. And I should remind everyone that we are trying to find f of 1 at the end of the day. But anyways, so how do we find this c? Well, we can just set this all right here. We just plug in f of 0, right? It's not too awful. So what we're left with then is 2 pi times the natural log of b divided by a plus c is equal to, well, actually the very same thing right here. So 2 pi times the natural log of b divided by a. And you'll see that these cancel, and at the end of the day, c does end up being 0, though it wasn't necessarily self-evident that that was so, because f of 0 was not actually, in fact, 0. So I just wanted to point that out. But now we can actually evaluate our integral now, because, well, all we have to do is plug in 1, because at the end of the day, scrolling up here, our t right here was just a 1 in the original integral. So what we can do is just, well, ditch the c, because that's 0, and set this equal to 1, so that term goes away, which leaves us with actually quite a nice solution. This means that our integral, say I, is equal to 2 pi over a times the natural log of a plus b. And that right there is the solution to our integral. I should be noted that a and b are just real numbers, just to point that out. But anyway, that are probably greater than or equal to 0. But anyway, I hope you all enjoyed this video, and I will see you in the next one. Thank you so much for watching.